Good afternoon. This afternoon we're going to be illustrating the use of AnyLogic to create an agent-based model that illustrates some basic structures that are common within the health economics field, namely the accumulation of quantities such as quality-adjusted life years, such as discounted and undiscounted costs, and such as the computation of incremental cost-effectiveness ratios for a model. We have other models which illustrate similar concepts within events and for system dynamics models. We're doing it here for an agent-based model. I've just created a new model within AnyLogic through File, New, and Model over here. But now that I've created it, I've right-clicked here, and I'm going to create a class called Person, which is going to represent my agents. I have to represent it using agents. And this is going to be an extremely stylized representation, since the focus here is on the cost economics components. So I'm going to create a state chart, which I'll call diabetes progression state chart. And I am going to create a first state, which is called normoglycemic. Because this model is so stylized, I'm not even going to be representing salient risk factors for diabetes. Next, I'm going to have a pre-diabetic state. Next, a case of full frank type 2 diabetes mellitus. Then I'm going to represent a rather severe complication associated with diabetes, end-stage renal disease. And finally, we'll have a transplant state associated with end-stage renal disease. Now I have to ask the forgiveness of those listening for the crudeness which I'm representing this. I'm going to have a transition to development of prediabetes, and we'll have a rate here with a time constant, say, of 2, so an average time of 50 years before they develop prediabetes on average. Once pre-diabetic, if there's no lifestyle changes and no other changes in their risk, they may progress on to type 2 diabetes. I'll give that a time constant associated with about 10 years, so a rate of 0.1, first order delay there. And then, drawing on some of the work we've done, I'll have a progression on to end-stage renal disease with a time of approximately 1/14 years. You'll note that indicating the denominator or the numerator as a floating point quantity here, specifically as a double quantities, is important that it not treated as an integer division and rounded off to 0. Then have a progression onto transplant, offering a hopeful time of about an average time of about an average time of about 5 years, but there's a competing risk associated with death, and here we have transitions from end-stage renal disease to death with a time constant that regrettably is very short, say 1/2.5 years. So an average of 2.5 years before someone dies from end-stage renal disease. absent transplant. But if they do reach a transplanted state, the situation is much more salutary. So, excuse me, I just added an initial state pointer. There was a mistake on my part. It was causing that odd coloring. So here we have a transition from transplant to death, which is much shorter, and we'll give that a time constant which is much longer. Time constant associated with that of say 20 years. Of course, an individual earlier in life is also subject to death, and I'll pull down states transitions here, which are associated with the mean life expectancy absent severe absent diabetes of 0.1, and I'll actually share that for but with a smaller time constant for pre-diabetes here. The rate twice that because of typical risk factors commonly associated with that. And finally, I'll duplicate that again for individuals who are with full frank 2 diabetes but don't progress onto end-stage renal disease. Very frequently, they're subject to other conditions that offer severe competing risks, such as heart disease, and I'll give them an average time to death of something on the order of say 8 years, so 1/8.0. Okay. This is a very, very simple state chart. Again, apologize for the crudeness of this depiction of what's a very textured phenomenon. But we do have individuals who are now progressing among these different states, which are chosen to illustrate some principles later. Now, we could, of course, add a variety of factors here, allow heterogeneity among individuals, etc., but I'm going to skip that in the interest of focus. I will add a representation of this individual, just so that we do have some way of depicting their presence visually. And I'm going to center them on the origin here, and that will be their depiction. You'll notice I'm being sloppy here. I haven't labeled these transitions. I could easily do that, etc. So now that we have these individuals, we will want to record some information associated with them. In this case, information that varies over time. So I'm going to create a variable here. There's many ways to do this, and my preference might be a different way, but for conceptual simplicity, I'm going to create a quality of life variable that's a double. Its initial value is 1.0. We're going to posit that when individuals come into a normal glycemic state, full blown as it were, they receive a value of 0.9. We'll retain a similarly high value for pre-diabetic. Type 2 diabetes, because of the significant impacts on multiple areas of life, will associate it with a lower quality of life, and end-stage renal disease being associated with a quite restrictive condition, limitations on some important activities, etc. I'm going to give it a lower state, but meanwhile, transplanted state, we're going to have a quite high quality of life associated with it. Say one comparable to diabetes. I think for just a little bit of texture, I'll add in a graph failure transition here with a with a timing of say, approximately once every 15 years, or on average, that will fail. So we have this quality of life, and excuse me, what I was doing. I'm going to assign to the quality of life variable in each of these places is what I meant to do. So we have quality of life successively equal to these values, which I had stuck in unthinkingly here. And that means that we can maintain the quality of life of an individual over time. Okay, so enough for now with the with the person. Let's go back up to main and let's create a population of people. We do that by dragging this person up here and creating a population. And associated with this this population could be header information on any parameters for them, etc. We're not going to make use of that, but we do need to indicate that it's a replicated population, and we'll give it a we'll create 1,000 individuals, say, within this population. That could be set by a parameter, which would then whose value will be established when it's created from an experiment. But for the moment, we'll leave it for simplicity as it is. Okay, having creating this population, we are going to compute statistics, some statistics across the population. One of them will be the cumulative quality of life across the population, which, if we total it up, will end up giving quality-adjusted life years lived. So cumulative quality of life across the population. This is a sum. What are we summing up? Well, we're summing up over all individuals, so condition is true, and we're summing up those individuals' quality of life. Okay. Now, we're then going to create a stock, which is going to accumulate the quality of life, quality-adjusted life years lived by this population, and overflow into the stock, which will be new qualities per year, which is in fact set here by that statistic. So population dot cumulative. This is the statistic we just created. It's taking a bit long to complete this, but cumulative quality of life. So we're calling this statistic, which we just defined on the population, to be the sum up of the quality of life across the population. And this can allow us, if we integrate this up over time, we can get cumulative adjusted life, quality adjusted life years lived to the current point. So let's just to illustrate this, let's actually save that. We can build it if we want to make sure that it's operating correctly. You should see build completed successfully, and now we can run it. So let's go run this, and let's see this basic subcomponent of the model. So here we have these totaling it up. So at year 2.78, say, let's stop time for a minute. By year 5.29, we've had 5,272 quality adjusted life years lived, and within the population, we have some people who have died, such as this first member. Some people who remain normal glycemic here. In fact, a large number of people who remain normal glycemic, and some people who are pre-diabetic. For example, this individual. And you'll notice that their quality of life differs on a per individual basis. Normal glycemic individuals are associated with a very high quality of life. So by circulating through here, we can get a sense of the population. And over time, as we run this model, particular individuals will progress. as time goes on, more and more individuals either pass away or progress on in terms of their diabetic status. Here we have a situation where some individuals have various different types of life status, and meanwhile, back at the level of the population, I'm navigating here among these different points. We do have quality-adjusted life years accumulating across this population. Now, if we run this out and we speed it up, you'll notice that this quality-adjusted life years, which appeared to be rising linearly at first, is in fact rising in sort of a curvilinear fashion, and to really see this in its with full clarity, we would need to establish a data set, which we could do here if we want to create a chart, do more than ad hoc look at it. So let's go create a data set here. So we look in the analysis area. Here we go, and we can create a data set. Excuse me, I don't even need to do that. I just realized data sets would be needed in a certain context, but we can actually just do a time plot. It would probably be the simplest way to do this. In this, we could create a qualies plot, and we'll have a time window of however long it takes. We'll have this updated automatically, and we'll add a data item to this, which will be in fact the cumulative adjusted life years as indicated in that stock. Now we do want to draw, if we do this once a year, we'll want to draw as many samples as possible. We could drag this out, and be nice if we give it a title. So qualies lived. Okay. So let's again save. It's good practice to do this compile. Make sure it builds successfully, as indicated in the lower left rather. And we'll run this again. And here we have a situation where we should be seeing values accumulate. Should have selected a smaller time frame there. I had forgotten just how that it uses that up front. You can see again it's curvilinear. This is running as fast as it can, and we have some very much older individuals here. Part of the problem is though that we've made an omission. You'll notice that if we run this model here, even though a lot of the population was, say, dead after a long period of time, say here we run it for 50 years. Oh, excuse me. So I'm going to switch to the main view here. So if we run it out to 50 years here, okay, so we're approaching that. If we go down and we look at individuals, we'll find that those particular individuals may be dead, but they're listed with the quality of life associated with the last condition. So what we really need to do is, when they enter this state, we'll treat them as, we either need to delete them from the population, or we need to treat them as having a quality of life of 0. We're going to delete it for other reasons, so it won't interfere with our measurement of life years lived. We're going to delete them from the population. So how do we do that? Well, we have to ask main to delete us. Now, the cleanest way to do that is to call off to main and say, hey, delete me. But in a violation of abstraction, we need to call up to get main and get population and ask remove underbar population, remove me from the population. Okay. So if someone dies, they're removed from the population. I'm going to go run this, and now what we'll see is something quite different. So the population size, you'll notice, is dropping here, and the graph has established a distinctly curvilinear form to it. Okay, so it asymptoted out. Okay, so having seen that, big picture, what we had is an individual, a set of life states, quality of life being determined by the states, in this case assigned to assigning to this variable. Just one way to do that. Another way, we'd have a function that, based on the state, returns the quality of life. It's probably cleaner. And when individuals died, we removed them from the population by going up to Maine, who takes responsibility for the population, saying, hey, remove me from this population. Let's embellish this a little bit in a straightforward way, and eventually we'll get to some more interesting stuff yet. So let's go add a measure of life years lived. So here we have life years lived, and maybe I'll, for kind of consistency and notation, I'll call it LY. And similarly, I'll have a flow that's new LYs per year, and new LYs per year is just going to be the size of the population. So if we have a population size 1,000 over the course of that year, there's 1,000 new life years lived. So we can call off, and we can do population dot, and this will be population dot, and we can go see, and we can ask for what is the size of this entire population, to return the number of individuals within that population. So here, what we're going to be doing is accumulating the number of individuals over time, essentially taking the integral of the population over time and using that for the life years lived. So let's go take a look at that. So if we run that, let's create a common graph. Let's go fix up this so it's not at length 1,000 time window. Well, given that a human life is measured in decades, I'll draw it out to 150 years, and now I'll copy this and paste it down below. And I'm going to call this life years lived. Okay, and we could have displayed it on the same graph, but this should actually be, to be consistent notation, it should be LYS. Okay, so this is life years lived, and let me spell it out. Life years lived. Okay. So again, it's a good idea to do this compilation. Let's go run this. Okay, and what we'll see here is rise in population, and we could speed this up, and you'll notice that both qualities and life years lived are rising and plateauing. You'll notice that, as you might expect, qualities which are adjusted as a coefficient by the quality of life are lower than life years, but both follow that same general trend. Okay, so this model just going on till time infinity is kind of distracting. Let's set it so that we have a stop time. We should make it stop at specified time, and have it stop, say, again after 150 years. I don't see much point going beyond that. Save, run. Okay, let's run it out, and running it at sort of full bore, as it were, and we can see them plateau at different levels. Okay. So fair enough. I'm leaving some more space for this for these axes on this side because they were getting truncated a bit. Okay. Good. So now we have quality-adjusted life years. We have life years. Maybe for sort of narrative consistency, we'll put those next to each other here. I'd like now to go add a more textured component, which is costs. And for this, we'll again be making very stylized assumptions. Specifically, we'll be assuming that there's some cost per year associated with an individual while in various states, and we'll be totaling up the cost per year based on across the entire population in a way similar to what we did with quality of life. So, for example, if there's 500 people, who are normal glycemic, and we assume no incremental costs associated with that, in 500 of end-stage renal disease, we would have, be accumulating on a per-year basis costs of 0 times the 500 in normal glycemic plus, say, the $50,000 a year it takes case it required for an end-stage renal disease times the number of people with that. That would be the cost that we're accumulating on a per-year basis. So if it was $50,000 and 1,000 people, and say 500 people, that would be $25 million exerted. So here we're going to posit that there are sort of costs exerted on a per-year basis by an individual. So I'm going to say, this is cost per year, and this is defined with respect to our model sort of frame with respect to some reference point. And I'm not going to go into this point more, but it's an important one. Presumably there's all sorts of costs these people are exerting in general, but we're going to be considering some added cost to that. So there's some cost per year that this individual is exerting, and we're going to assume that in the normal glycemic state that the cost per year are in fact 0. These are Java statements that are here. They're sort of sentences in Java that tell it something to do something, to perform some action, as opposed to an expression which tells it to calculate something, merely to calculate something. Here we are telling it to undertake this assignment. We need to follow them by semicolons. Okay, so here we have a cost per year in a normal glycemic state. We're going to assume in a pre-diabetic state that individuals impose some quite modest costs, perhaps associated with that thing. Let's say $100 a year for type 2 diabetes. Full frank type 2 diabetes will assume administration of drugs such as metformin, possibly even quite possibly use of insulin these days. I'm going to associate a cost of on a per year basis of say $2,000. Now, with end-stage renal disease, we may have very, very significant costs involved. Let's suppose $50,000 per year. This varies a lot by healthcare system, and then in the transplant situation, we're going to have costs following transplant that are actually quite textured and articulated based on how long it's been since you have had transplant. We could easily divide this state into several states. I'm going to sort of amortize that over all, and we'll assume a cost per year of something like $20,000, $2,000, excuse me. Now, we're at this point we're omitting an important cost, the cost of the transplant event, and I'll come back to that. But I just want to bring this principle through of sort of this cost per year that are exerted by people in the population, and we can total it up across the population in a similar form. So here we have a accumulated cost stock. Okay. Accumulated costs, and we're going to create a flow into this. So new costs. Now, I don't like the fact that this is kind of overlapping on the left with this other one, so I just want to see if I can drag this. Oh man. So put this in truculent. Okay. Okay. Let's well, that should be suitable actually as it is. Let's just move that. Oh my gosh. Okay. We're gonna move this back, and we're gonna move this arrow back too if we can. Okay. Oh gosh. Oh well. Is there any way we can get this thing to kind of move nicely? Well, evidently it's being somewhat truculent. We could try to sort of futz with it here, but I'm gonna try to. I see it's gonna drag this whole darn thing. Okay. Yeah. Drag this guy over. Okay. Well, that was more successful. And okay. Now we have cumulative costs being totaling up. So cumulative costs is an integral of new costs. The key question is what is new cost and how does it depend? Well, we're going to here total up the costs per year in the population, and the easiest way to do this is to have a statistic in the population here, and so we're going to do cumulative. Let's call it new costs per year. And here what we're going to be doing this again. We're going to be summing up over all members of the population, so this is true, for each person is called item. We're going to be asking for their cost per year, okay? And it's being truculent, but cost per year, okay. So let's do this build here. It's causing trouble. I think I may have called this costs per year. We could certainly easily look, and there indeed it built successfully. I could have easily checked it with this guy here and expanded variables. Okay. So here we have a statistic now, which we've defined at the population level, and basically given a recipe for how to compute this thing called new cost per year. So now this flow here, the value of this flow is simply the new cost per year. So we have to give this formula for this flow. Now, it's population that knows how to compute those new costs per year. So I'm gonna this is something we say, hey, population, compute new cost per year. Okay, that's an expression we give it. It tells it how to compute that. Compile it. Okay, so now we're in pretty good shape. I'd like to create another time plot here, and so I'm going to just copy that one and pull it down here, and so this is cumulative undiscounted costs, okay, and here what are we going to display? We're going to do cumulative So this, we should call it, I think, cumulative costs. Accumulated costs is what we called it. Now, to be kind of more specific, I'm going to call it accumulated undiscounted costs. Okay. So these are the costs that are we don't take into account the time value of money. We're not taking into account discounted cash flow. In other words, net present value. Instead, we're just accumulating up in sort of a naive fashion the undiscounted cost. So all we do is we total that up and let's run the model. It's good practice to sort of frequently go and build your model. And you'll notice that we have these costs up here being accumulated. So in individuals or in other states, different states, we're accumulating different costs by those individuals. And here, as time goes on, we have quality of life to max out, but costs continuing to rise faster than quality of life. Why are they continuing to rise? Well, they're continuing to rise in part because because as people age, more and more of those people who are remaining, there's fewer and fewer people remaining. Hence, for example, these life years lived almost plateauing. Those people who do remain are developing more and more serious forms of diabetes, and hence exerting higher and higher costs. For example, they may have be an end-stage renal disease, and in any case have developed symptoms sufficient to exert some costs. So here we have quality adjusted life years lived, and cumulative undiscounted costs. You may have guessed what's coming next, which is taking into account discounting. Now, we can actually perform the discounting in several different ways. This is typical in AnyLogic. We're going to do it in one way that maybe makes greater use of formulas that may be familiar to my listeners, but we could explore this in different ways, such as with a discount factor that's in fact evolved over time according to different potentially varying discount rates. So here we're going to have new discounted costs. Now, in contrast to the sort of new costs flow above, new discounted costs is going to depend on, for sure, on the new cost per year. But it's also going to depend on a discount rate, a discount coefficient. And to make this explicit, what I'm going to do is, within system dynamics, I'm going to create an auxiliary variable here, which is going to be called discount factor. Okay, and this discount factor is going to be defined as e to the minus, and we're going to have some discount rate times the amount of time that's elapsed from the beginning of the simulation. So to make this just a little bit less heinous, I'm going to create a parameter called discount rate. This is a parameter, so it will be specified when main is main, where sort of global environment, the stage in which the agents move around. When that's created by a simulation, we'll specify the discount rate that will allow us to kind of vary it. And discount factor here is going to be e to the minus the discount rate, or that's expressed on a per year basis, times the number of years since the simulation started, which we'll assume the time unit is years, and so we can just ask for the current time. Okay, so given that we have that, we'll make this quite explicit. We'll have a this new discounted cost depend on the discount factor, and it would be nice if if more than that, we had the discount rate, the discount factor's dependence on the discount rate be clear. Be nice also if we could depict time, but I'm going to skip that. So we have this discount factor. The theory of discounting is associated with net present value. It reflects the fact that a growing bit of money now in the bank, say $1,000 in the bank, it grows over time. So if we have this sort of dependable investment vehicle, a larger amount of money in the future is worth a lesser amount now. We can turn a lesser amount into a larger amount in the future very easily by investing it in a reliable investment vehicle. So if we think in present value terms, when costs are exerted in the future, we could plan for them, or in the now, by putting money in the bank now that's much smaller than the cost that may be borne, say, 50 years from now. So we undergo discounting to reflect that. Costs in the future are discounted to reflect the fact that if we speak in present value terms, they're worth kind of less in the present value, because we could anticipate them in a way and plan for them, and by devoting less money now to pay them off a large amount of money later. I won't go into that. It's a rich and interesting area. So we have this discount factor. We have this discounted cost here. And these new discounted costs depend not only on this discount factor, not only on this discount factor, but also on these population these new costs per year exerted by the population. So new costs up here, undiscounted costs only takes this into account, whereas this new discounted cost needs to multiply it by a discount factor. Now, we'll specify a default discount rate according to convention, common in certain areas of the world as 3%. And we'll go run our model. So now we have discounted costs accumulating and undiscounted costs accumulating, as might be expected. The discounted costs are amount to less than at the same time as corresponding undiscounted costs from the same time. I'm going to copy this here so we have a nice graph of it, and this will be cumulative discounted costs. Okay. And oh gosh, this name is so quality. So this could be discounted costs plot. Normally with these models, this should be accumulated discounted costs. We can have AnyLogic help us here. Accumulated discounted costs. Okay, it's the value of that stock that we're playing. In this here, normally I allow some, I'm not very picky for these pedagogic models, but it's just risky to leave these things named so badly. So undiscounted cost plot, and based on the fact that was there, I'm guessing that even this life years one is not named properly. So this would be life years plot. Okay. Fine. So we should be able to compile that, build successfully, and we can run it either by right-clicking here or using this button up here. Okay. So let's go do it on the screen here. So here we have cumulative discounted costs, cumulative undiscounted costs, all are rising. Pull this over so you can get some sense of this, and as can be appreciated, the discounted costs are significantly less than the undiscounted costs. We're getting some truncation here So I'm going to clean things up a bit. Some of you might encounter this, and it's useful to know where that's coming from. First of all, I'm going to make this a bit larger, and then I'm going to make this guy a little bit, leave a little bit more space on the left-hand side, particularly for where there are these larger numbers involved, because it's all too easy for them to get truncated. Okay. So let's go here, and maybe we'll maximize this, and now we can see with greater clarity what these numbers are. They're going to be growing quickly, though. So we have a population. Number of life years lived is rising, but plateauing. Unfortunately, the costs continue to rise because of diseases of aging, in this case diabetes and end-stage renal disease. So here we go. Discounted costs are quite a bit lower, $8 million compared to $25 million here. And here we have the life years lived and quality adjusted life years lived. Okay. So here we have a very simple model with a population, and maybe just to kind of illustrate the underlying dynamics a little bit more suitably, I'm going to create again one of these plots, and I'm going to display a more fundamental variable than we've been looking at, namely the size of the population. Let's give it afforded a bit more room. And this will just be population size plot. And in order to get the value for this, we have to ask, hey, for the population, how many people are there in the population right now? So population.size. You'll notice here that number of elements in it. So here we go. Number of elements in the population. Notice the others could just plot the values of these stocks, but here we're plotting the number of individuals in the population. Okay, so here we have the number of individuals in the population. You notice it's declining over time. And I again apologize for the stylized version of this model. Obviously, we could put in age-specific hazard rates for death or diabetes, and do all sorts of work to make it more sophisticated. Here we have fewer and fewer people over time, but those fewer and fewer people are in more and more serious health states, hence the costs are rising. But we have discounting going on as well, so the costs are kind of more quickly plateauing in terms of discounted costs than they are in terms of sort of undiscounted costs. Here's the life years lived, however, very much reflective of the population. The increment here, the derivative of it being reflective of the population size. Okay, now I could go into creating different scenarios. For example, with a lower discount rate. This would be a very straightforward thing to do. So we go and we add an experiment, call it low discount, low discounting, and we're going to add it in. And the salient difference will be that while our original scenario, or baseline scenario as we say, while it had parameters for discount rate, which are the default parameter, for this low discount rate, we'll use a much lower discount rate. And we could run that, and we'll see a difference, not so much in the other factors up to stochastics. They should be the same. But what we will say is a different level of discounting relative to this value here. In short, will sort of weigh more highly costs borne later in the simulation, and we'll see the discounted costs be relatively closer to the undiscounted costs. You'll notice the model runs faster towards the end because there's fewer people to simulate. There's less work to be done, fewer moving parts, and therefore can simulate more quickly. Okay, So we've just shown a model that accumulates many of the basic statistics. However, the most gnarly and sort of awkward component has really not been achieved. But this missing component is one of the most critical ones, and that's computation, say, of an incremental cost effectiveness ratio associated with some intervention. I'd like to introduce an intervention now, so that we could actually have sort of a plausible intervention. Right now, we have everything pretty much hard-coded in terms of people's rates of progression, and there isn't a lot of give here in terms of prevention of diabetes. That's because these rates sort of progression to prediabetes are fairly well established. So, well, let's suppose that we could catch some of those people with prediabetes early on. It would be good to distinguish between those who are recognized pre-diabetics and not. But imagine if we could, through some sort of intervention, have a situation where we could draw people back with a pre-diabetes sort of intervention rate. So we have some rate of, when you're pre-diabetic, of going back to a normal glycemic state. So so we'll call it the in a sort of using crude terminology, pre-diabetic prevention hazard. I'm using hazard here in the sense of chance per unit time. And the idea is that sort of prediabetes prevention rate. The idea is that maybe through some intervention we could prevent diabetes from occurring. Again, apologize for this, but we'll actually go and create a parameter now for this prediabetes prevention hazard. We're going to create at the individual level, so it could vary in a heterogeneous fashion. But the idea will be that we'll be able to examine the possibility of sort of raising it or lowering it. Okay, so thinking about this, I'm actually going to we could allow this to vary on a per person basis, but because it might be confusing to people, I'm actually going to have it just vary once for the entire model. So the idea is we'll have a particular scenario, and we'll have some prediabetes prevention rate. Okay, so we have now a prediabetes prevention hazard here, which will be a parameter in addition to the discount rate parameter. Discount rate parameter, I think, was down here. I kind of like to put them together, but I'll put it over here. As is sort of common convention, I'll put it off the screen if I put it over. Yeah. Now it's gotten separated from its head. Okay, there we go. Okay, prediabetes prevention hazard, and I'm going to set it to be by default 0. We'll allow for interventions which do set it. Now, since we moved it to main, a person's going to have problems because it can't find it. It doesn't know where it is. When we tell it that there's a rate to go back from prediabetes to normal glycemic, it doesn't know where to find it, and that's because it lives in main. It doesn't live here. So we have to ask ourselves, hey, get my associated sort of main class and get the prediabetes prevention hazard from that. Okay. I apologize if this is confusing. The point is, certain things live in main. By putting this parameter in main, we allow it to be more easily set by an experiment. And I wanted to spare you folks the need to create parameters at two different levels. But one offshoot of that is, if this parameter lives in main, we have to get it from main. So we have to ask ourselves, if I'm a particular agent, a particular person, I have to say, hey, get my associated main class and get the prevention hazard associated with that. Okay. Now, for software engineering reasons, that has some unpleasantness associated with putting it there, but that's where I'm going to leave it. And now, associated with each of these things, we have this simulation. Maybe we'll call this simulation baseline. Okay. That will have a prediabetes prevention hazard of 0. Similar to low discounting, I'll call it low discounting baseline. It also will have a prediabetes prevention hazard. But then I'm going to introduce a parameter here, a scenario here that's an intervention scenario. Okay. So it's an experiment I'm introducing. And I'm going to say aggressive prediabetes prevention. Okay. You could argue whether it's prevention here or forestalling, but we'll give it a prediabetes prevention hazard that once they're pre-diabetic, we're going to go out and actively screen for them and try to prevent them. So on a per year basis, they have say a 25% chance. So on average, it would take 4 years to prevent them. So now we have a baseline, and the baseline we've seen before. That's just the one we've run before. We introduced the prediabetes prevention hazard, but its default value is 0. So for the baseline, it's 0. It's the same old that we had formerly. So I'm gonna run this, and we'll see the differences. The same basic factors that we saw earlier. Remember, this is with the 3% discounting. Model speeds up as there's fewer and fewer people to be simulated, and again we have somewhere around 9.6 or 9.7 discounted cumulative cost. Life years, cumulative adjusted life years lived, somewhere around 42, 43,000. Okay. Okay, now let's go to the low discounting baseline. The salient, the aggressive prediabetes prevention. Here we have the same discount rate as in the baseline, but we have a diabetes prevention initiative. Prediabetes prevention initiative. So let's go run that, and let's go see what results there. Okay, so here I go. Again, want to emphasize the discounting is the same, but what we have is we have some people who are developing prediabetes going back. Some people developing prediabetes going back, and in fact, there's a pretty good chance if you develop prediabetes, you'll go this way instead of going on to frank type 2 diabetes. So here was the result of our scenario. You'll notice that it was running while I was showing you the individual level view. You'll notice that quality adjusted life years lived are significantly higher. They went up from something like 43,000 to something like 58,000, something like that. And cumulative discounting costs is significantly lower. It was up upwards of 8 million, and now it's between 3 and 3.5 million. Maybe it's about 3.4, 3.35 million. So we've really saved money, and we've saved quality adjusted life years lived. Or so we might think from sort of the individual level perspective here. But of course, programs cost money. So we might have some costs per year, so for example, borne by this program that need to be factored in. How would we factor those in? How would we consider those as well? If we want to consider the fact that this intervention costs money, say either on a sort of overall staffing level, or at the level of sort of maintaining a program, how do we take that into account? Well, it would be nice if somehow we could add things in to the sort of accumulated discounted costs here. Sort of increment this, say, for each case of prediabetes averted. That might be something we could do. But maybe there's some sort of program costs associated with this. I'm going to change this where it says new costs here. We could have new health services costs, but then we could have new new costs associated with intervention delivery. So this would be new intervention costs, okay? And I'm going to drag this down to here, and we'll place this here. So we're going to have new intervention costs. And we might, for simplicity, we might say, well, if a prevention program is in place, we'll just estimate what the costs are per year associated with that. So this would be costs per year associated with the intervention. So costs per year, so intervention costs per year, and by default will be 0 in the baseline scenario. But if we have an intervention, we'll need to specify it. And then the new intervention costs will just total up intervention costs per year. Okay. Now it looks like an unhappy camper there. You'll notice sometimes it complains more than it needs to. Excuse me. No, it's seems to be actually onto something here, perhaps. Intervention cost is used but not expected. Okay. Okay, well, you need to get it over there by sort of please the system dynamics sort of visual diagram gods, as it were. We're gonna go and actually sort of link it in visually. Oh gosh. Okay, it just separated its head from its tail, so to speak. Let's get it back here and drag it over. Okay, now it's more truculent. Okay. So we're gonna drag this up here, and okay, well, we're gonna hitch it up to that, and then we gotta drag this thing. Come on, drag it down there. Okay. By this little handle here, we can actually route this around. Okay. So it's an intervention cost per year, which is a parameter, and this guy depends on it. It was just complaining that there's no connection between these two. Even though logically it knew this thing depended on that, it wanted this visual connection to communicate that. Fair enough. Okay, so for the baseline, we because we set that new parameter, intervention cost per year, to have a default value of 0, the baseline is aware of that. Here, the intervention costs per year, we're going to assume that intervening actually costs some numbers of dollars per year. Now, we're making a very sort of simplistic assumption here that our program, is maintained at a certain level regardless of the size of the program, and we could make this dynamic. We could actually have it have a per capita intervention cost per year. Well, okay. Why don't we go ahead and do that, because that's much more plausible. So for each normal glycemic or diabetic person in the population, say for each normal glycemic or diabetic or pre-diabetic person in the population, there'll be a cost per year. So we're going to actually need to do a little bit of fancy footwork here. First of all, this is no longer going to be simply a so this is going to be a per non-diabetic capita intervention cost per year is going to be the name of this. Now there's then a cost borne per year. And that depends on the population size. So intervention costs per year is in fact now a dynamic quantity. And what is that dynamic, on what is that dynamic quantity going to depend? Well, it's going to depend on, in fact, this per non-diabetic capita intervention cost per year times the number of non-diabetics. So this intervention cost per year is going to be this per non times the number of non-diabetics in the population. Okay, now how are we going to get that? Well, we're going to have to compute a statistic. Over here in the population, we could go add a statistic. Now, statistics don't tend to scale very well once you start breaking the population down by many different things, or if you're calling them very frequently, but for simplicity, I'm going to show them here. I'll try to have another video on artful ways to sort of lower the cost of statistics. Might be able to do that within my coming boot camp. Okay, so here we're going to have the count of non-diabetics. Okay, this is going to be a count, and the condition here is that how do we tell someone's non-diabetic? Well, let's go look at person. They're either a normal glycemic or they're in a pre-diabetic state. Okay, so that's what we want to sort of clue off of. So here, count of non-diabetics. Either they're in a is state active. Okay. What's the name of that state chart in person? What is the name of those components? Normal glycemic. Okay. So, and the name of the state chart is diabetes progression state chart. Okay. I apologize, I'm going back and forth there. Is state at, so we want to ask for that population member, their diabetes progression state chart. Okay. We want to ask, is the state active? And what state do we want to ask about? Well, it's a state with respect to person of being normoglycemic. So we'll count a person if they're normoglycemic, or we'll count a person if they are pre-diabetic. Okay, pre-diabetic. Okay, so either they're normoglycemic or they're pre-diabetic. So what is this thing here? Well, this is basically saying, okay, we're going to count someone in this statistic under certain conditions. We're counting up the number of people who match some criteria. For each person in the population here called item, we're going to ask their state chart, keeps track of their diabetes status. Hey, are they in a normal glycemic state? Why do we need this person? Well, turns out that we could have people, we could have dogs, and dogs could undergo diabetes too. In fact, they do in the population. Here we need to say, okay, we care about normal glycemia with respect to persons. This is, at technical level, this is what's called a static constant variable of person. So it's an attribute of personhood, the fact that they have this sort of normal glycemic distinction. So we're asking, okay, are we going to count this person? Well, we'll count it under one of two conditions. Either they're normal glycemic, in other words, they're in their state, normal glycemia, in their diabetes progression state chart, or they're in their state of being pre-diabetic. Okay, so we just built, and that's fine, and this is called count of non-diabetics, and that's what this is totaling up. It's going to be totaling up. So here, in terms of the intervention cost per year, we have an intervention cost per non-diabetic person for sort of screening that population. As the population shrinks, people who are not yet diabetic, our costs there will go down. And then we'll have we'll sort of go and ask the population, hey, how many people are non-diabetic, and multiply it times the cost per year cost. So now we have costs that are varying on a per year basis, okay, as the population shrinks, of non-diabetic shrink, we'll have lower and lower costs for screening, for pre-diabetics, and for counseling them. And then we're going to have a cost associated with new. We're going to hitch that up, so the new interventions depend. The new intervention cost per year depend on this intervention cost per year. Okay. We could quibble with this. We could say, well, the dominant cost would be for the pre-diabetics themselves, to have a lifestyle change effect, and not for both pre-diabetics and for normal glycemic. But there's some screening costs associated with them, so I'm just going to leave it. We could have two factors to this cost: one, a screening cost per person, looking for the person, and then one, a lifestyle intervention cost, which would be fine to do. And I think I'll actually go ahead and do that, because it's so tempting to do. So here we have a count of non-diabetics. Then we have a count of pre-diabetics. Sure. And how do we tell if a person is pre-diabetic? Well, it's just the same criteria we used earlier. So we can actually reuse this criteria. Okay. Again, this doesn't scale very well once you start doing things. We're counting up the number of pre-diabetics. So we're going to have a cost per non-diabetic. So this is essentially per non-diabetic capita intervention screening costs per year. That's what we'll call it. And then what we'll do is we'll have a cost per non-diabetic, costs per pre-diabetic lifestyle intervention cost per year, and that will contribute some cost as well. What will the cost be associated with that? Well, we're going to total them up here. So this will be a lifestyle change intervention cost per year. Okay, and we're going to go and put this associated with that, and so we have costs associated once we found a pre-diabetic actually getting the change, and then we have some costs associated with screening. So these intervention costs per year, this would be intervention screening costs per year. That depends on this per non-diabetic capita intervention per non-diabetic capita per intervention screening cost per year times the number of non-diabetics. This other one is this cost per diabetic lifestyle intervention cost per year times these costs per pre-diabetic lifestyle intervention costs per year times the number of pre-diabetics. How do we get that? Well, the population, we had set up that statistic, so count of pre-diabetics. Okay, and now, since we have this cost extended from screening, and costs extending from actually performing an intervention, we can add the 2 per year. Okay, so we add up intervention screening costs per year plus lifestyle change intervention costs per year. Those names could be improved, but fundamentally we have these 2 types of costs. We'll assume that each type of cost is by default has a value of 0. So in other words, for an intervention, there's going to be some cost there. Okay, so big picture here, what do we have? We have now have added to the model consideration not only of health services costs on the one hand, but now we have these further costs associated with intervention, and there's 2 types of costs we totaled up. One is the costs associated with going and finding people in the population, and one associated with intervening on those people who are found. This cost of intervening reflects pre-diabetics only. This cost of screening for people reflects kind of all non-diabetics. We're looking out there, all people not known to be diabetic. Okay, so we have the baseline, and the baseline, because we set those parameters to have values of 0 by default, they have no costs associated with them. But this aggressive prediabetes prevention, we have some costs of per capita intervention screening, so that's for non-diabetics. And then we have lifestyle intervention changes, which we'll assume will cost, $1,000, say $750 per person per year. The screening costs on a per person basis, maybe it won't be $100, maybe it will be $25 per non-diabetic per year. Okay, so we now have in our model taken into account intervention costs as well as costs exerted on the healthcare system. Now this is complaining, so there's something that's troubling it. Let's go see what it is. So it's actually not giving us any message down here, but it's sure showing an error message associated with something. So let's go follow this red X, and it says method count of non-diabetics. It is undefined for this. So why is that undefined? Count of I had been missing an S. It was count of non-diabetic versus count of non-diabetics. Okay, we built it. It built successfully. Now we're in good shape. So let's go look. Well, the baseline is the same as ever. We haven't changed anything in the baseline. These costs aren't born for the baseline, the intervention costs. We haven't changed those other costs exerted through the healthcare system. So what gives here? There's going to be actually no change. So if we look, we'll see the same basic numbers we did earlier. So as the population dwindles, once again, it's going faster. It's actually slower down right now because it's actually calling to get the number of people in the population much more frequent. But you'll notice we're seeing the same upper about 9 something million in cumulative discounted costs, and quality adjusted life years lived is maybe about 42, something like that. Okay, let's go look at aggressive prediabetes prevention. We had posited that this secures a 25% chance per year that you're going to prevent people from going on to diabetes. And now we've imposed these costs. Let's go see. I mean, we're preventing people from going from diabetes, and we had actually achieved quite a reduction in cost because of that before. But now if we take into account the intervention costs, how are we doing? Now we're having intervention costs on a per year basis, which are accumulating, which can be fairly substantial. They're going down over time as we have fewer and fewer people, but they are quite substantial nonetheless. And we also have these health services costs here that are still accumulating. Interestingly, the curve is more textured. It's notable, of course, that we're getting people to live longer, and because of that, they may be they're living longer in the population, so it takes longer to run, but they're typically living longer in the state without diabetes, not yet being diabetic. Okay, so we still have, despite the costs associated with interventions, we've still managed to bend the curve associated with cumulative discounted costs, and we've also still managed to raise the cumulative quality-adjusted life years. Now, if we had changed the aggressive prediabetes prevention, and if it costs more for a lifestyle intervention, let's say cost several thousands of dollars for that, and if the screening cost more, then we might see something quite different. So here, if we had posited a very expensive program and screening costs that are fairly high for those in the population to secure that level of aggressiveness, we would be actually looking at considerably higher costs associated with it. And notice now the intervention costs are actually here dwarfing the health services costs. We see quite rapid rise in this aggressive intervention. We're keeping people healthier for longer. We're probably going to be preventing quite a number of cases of diabetes. That is, people will die before they develop diabetes. On the other hand, that comes at a cost. Costs in terms of preventing it. Once again, we are seeing sort of very, very significant intervention costs remaining here. But you'll notice that the costs do remain still rather low and rather modest at the 150-year time frame. We have some sort of Methuselah's living a very long time period. Okay, so even a highly aggressive thing and imposes a cost. Okay, now let's suppose that we were to want to expand this by considering costs that are sort of event costs. Thus far, we've been considering costs that are sort of costs associated with cost per year being in a state. Let's suppose we wanted to have a cost associated with something like a transplant operation. Instead of trying to amortize that across post-transplant state, let's suppose we want to take into account the actual cost of a transplant operation. Now we might hope, on the face of it, that we could simply add values in to the sort of when this occurs, we could add a value into the accumulated, say, undiscounted costs of the cost of the transplant operation, say a full $75,000 associated with this transplant operation. It might not be a reasonable, an unreasonable thing to sort of hope for, and we could try that. Indeed, you'll notice that it did allow that. So here, when a transplant occurs, we can actually we actually increase the value. So just to make this point more clear, I'll have value the accumulated, so I'm about to receive a transplant. The accumulated undiscounted costs prior to the transplant are, and I'll report those here. And now, following the transplant, I have received a transplant. And the accumulated costs post-transplant are, and we'll report it. And if it's working, we should see that those differ by a factor of $75,000. So, given individual undergoing the transplant has now imposed this cost on the medical care system associated with the transplant of $75,000. So we'll run this this on here. Time is running on, and you'll notice here that we do go up from here. This is 3.4 million, and then it rises to about 3.5 million, with the difference being $75,000. Closer. I speak in approximate terms of the actual values. So here it goes up from, for example, 5179 to 5254, and there's a difference of $75,000. So here, individuals have imposed additional costs. Where did they put it? This accumulated undiscounted costs. Well, that's over in Maine here. They've just added their value to this by virtue of receiving this this transplant. Now, how about accumulated discounted costs? Well, we're going to need to take into account this discount factor. We're going to need to multiply it there. So we can do basically the same sort of thing. There's prettier ways to do this, but for a didactic perspective, I just want to draw attention to the idea. So here, for the discounted costs, we need to multiply 75,000 times the discount factor. Where does the discount factor live? It lives in Maine, so we can multiply it times this discount factor. Okay, now that we've sort of shown this works, I'll comment these guys out. And so here we're incrementing by this event. When this event occurs, we increment it not by a cost per year, but by a cost for that, in this case, that operation, and then increment this discounted cost by this operation times this discount factor. Now you'll notice we still have these sort of costs per year for post-transplant, and I'll assume that these are lower. I sort of mumbled about amortizing the value of the transplant there, so those costs are going to be lower. Okay, so now we have a baseline which does different because we now have taken sort of transplant-related costs in, and we have costs accumulating now, not only through these two flows, but also directly into these stocks by virtue of the events. So I want to highlight something. Before, we were taking into account per year costs associated with these costs of intervening with sort of screening for people, and costs associated with sort of supporting people in various health states. Those are per year costs. We multiplied times the number of people, and we're applying them to get the cost per year across the population. Here we have events, and these events occurring at certain rates, number of events per unit time, and we have a certain cost being imposed by a given event, and thus we have sort of cost per per year, total cost per event times the events per year, is sort of also accumulating into here. And you'll notice that it has actually nudged up the transplant costs. Consideration of the transplant costs in a non-amortized way have sort of nudged things up, although they haven't changed the quality-adjusted life years lived. Okay. So in short, we have taken into account a bunch of common factors, taken into account quality-adjusted life years, taken into account life years, this discounted costs, these undiscounted costs. We have taken into account several types of costs in particular, most notably sort of costs for being in a state on a per year basis, and total is up across the population, and then also event costs and costs associated with the transplant. So we've taken a variety of costs into account, and we've accumulated them at this global level and provided feedback on them. And we've examined the impact of interventions, which we, in a stylized fashion, showed as modifying those costs or modifying sort of the risks associated with particular people. I would welcome you to come back for a second video, which continues this subject, where we extend this model to examine the impact of doing incremental cost effectiveness calculations, which compare a baseline on the one hand to an intervention scenario on the other, and look at incremental cost effectiveness ratios with those. Thank you very much. I hope you found this of help.